Good evening, everybody, and welcome. Thank you so much for joining us this evening for our presentation. It is the first of two talks and hosted by First Congregational Church of Akron. My name is Reverend Nanette Pitt, and I'm the senior pastor here at the church. And it gives me great pleasure to welcome each of you here tonight into this virtual space, but especially Dr. Eric Schreiber, who's joining us as our guest speaker tonight, and I know we're all very eager to hear what he has to share. We are making a recording of tonight's presentation to make available to a couple of the people who expressed interest in the presentation, but who were not able to attend this evening. So I wanted to begin by letting those of you who know, because I know that we're welcoming some members tonight and we're welcoming some old friends and some new friends into the space. So I wanted to let you know that Akron, Akron has been blessed with a beautiful environment, as all of us know and cherish. First Congregational Church has been situated in 5 different locations in downtown Akron since 1833. So we have a long history and are very invested in what happens here in our local area. But we also feel the call of our faith, as we understand it, to care for creation. And each year we have a season of creation around the time of the start of the fall, September into October. And this series rounds out this year's season of creation as we try in our faith to take seriously our responsibility to care for the earth in a thoughtful and educated way. So we're making an effort tonight to educate ourselves, and thank you again to all of you for joining us. So we're having a series of 2 talks, and tonight, of course, you know that we're hearing again from Dr. Eric Schreiber on climate change and emergency in slow motion. And then next week at the same time on Wednesday evening, we will be hearing from Rob Curtis, who is here with us tonight in the group, I see. Welcome, Rob. We look forward to seeing and hearing from you next week. And want to invite everyone to join us again for that. And we'll put in the chat the link to register for next week's talk. And that talk is going to be Gardening for Biodiversity and the Half Earth Project, which is a wonderful project well worth supporting. So we'll make sure that this evening, if you follow the chat, and I'm going to highlight the chat for you too, so that you know it should pop up. It should already have popped up for you with the register for a talk on October the 27th. You can follow that link to register for next week's talk, again on Zoom. And then also just want to do, again, you'll see the chat pop up if you weren't looking for it earlier. And that's the way that we're going to be asking questions tonight of Dr. Schreiber. We're going to keep everyone on mute and hear from Dr. Schreiber first, and then please use the chat to type in your questions, add your questions, and then we'll save those till the end of the presentation and pose them and engage that way in some dialogue and conversation. I wanted to, having that housekeeping out of the way, introduce you to Dr. Schreiber. He is fascinating, lives in the local area, up in the Cleveland area. So we can't quite claim him, but we can claim him well enough here in Akron. And Dr. Eric Schreiber is a retired diagnostic radiologist. And that doesn't sound like it has much to do with the environment, but I really appreciated when he shared with us that he first became aware of global warming years ago during his study of physics and chemistry as an undergraduate student, and it really spurred him to begin to think about what was going on in the world around him. And the serious nature of the problem became more apparent to him in the 1980s, and he has been a student of this subject, offering talks, and has now become a relative expert. And so we are really grateful to you, Dr. Eric Schreiber, for having you with us. And I'd also like to recognize and greet your wife, Jessica, who is with us here supporting tonight. And we appreciate the work that you're doing in this area and all of the information that you're to bring us. So without further ado, I'll hand over to you.
Well, thank you very much, Reverend. I guess people will wonder why a physician would be have an interest in this, and it's related to public health. The thing is that a physician treats and hopefully does good for one patient at a time, whereas somebody who's in the public health field is dealing with hundreds or thousands or even millions or billions of people. And climate change, I believe, is perhaps the most important public health issue. It's insidious, and what it does is it multiplies all the other public health issues. So I'm going to move over to a slide deck here, and that will take me a second. I want you to bear with me as we go here. And I'm going to take over the screen with my presentation here. So unfortunately, in the course of 1 hour, we cannot cover everything. There are so many topics. Each one of the topics on this list could easily take up an hour. And we can't, a lot of these I will touch upon, some of them I won't get to at all. But I do want to talk about some of the terminology that I'm going to use during this talk. Weather and climate, there's frequently confusion on this. I love to use a baseball analogy. Consider Babe Ruth. Babe Ruth was unpredictable when he came up to bat. Two frequent occurrences were a home run or a strikeout. And that is equivalent to the weather. You find out what's going to happen the next time the Babe is up to bat. His career batting average was 342. That's climate. So global warming is a phenomenon that's not necessarily bad. Global warming occurs when heat is trapped by the atmosphere and the earth is warmer than you would expect it to be. But what has happened recently is that global warming has increased at a rate that is unprecedented. Climate change are all the effects from global warming, like floods and drought and sea level rise and all of those things that we hear about. That's climate change. Fossil fuels, those are the coal, the natural gas, the petroleum products that are mined. They are pulled out of the ground. They've been sequestered for tens or hundreds of millions of years, and suddenly in geologic time, we're pulling them all out of the ground and igniting them, essentially at once, producing carbon dioxide. Greenhouse gases are the gases which in fact trap heat, and we will be getting into more detail about that. Carbon dioxide is, spoiler alert, it is the most important of the greenhouse gases, and methane is the second most important. ppm stands for parts per million. It's a way of quantifying a gas that is a small quantity in the atmosphere. For example, the gas argon constitutes, about 1% of the atmosphere, the air that we breathe. So we talk about argon as being 10,000 parts per million, or 1%. Carbon dioxide, on the other hand, is about 419 parts per million at this point. So this talk has 6 parts. We're going to talk first and give examples of the chaos that we've been seeing with the weather and the climate. We'll talk about public health issues and then a brief history of climate science, really to emphasize that this is not something new. We've been we've been talking, humanity has been talking about and writing about the climate for several hundred years. We're going to talk about the biggest problem, which, spoiler alert, is carbon dioxide. And most importantly, we're going to be talking about solutions which already exist and what we can do to try to make change in the way things are going. So let's talk about the chaos. You may have noticed, of course you've noticed, that the weather worldwide is becoming increasingly chaotic. You can't turn on the news without seeing evidence of that. I want to talk about what are called tropical cyclones. And these are the various names that we have for the storm, which is a tropical cyclone. It's more of a geography thing than the nature of the storm. A hurricane is a tropical cyclone that occurs off the east coast of North America and to a certain extent off the west coast of North America. Typhoons are tropical cyclones that occur in the Pacific Ocean off the coast of Asia. And cyclones are tropical cyclones that occur in the Indian Ocean or anywhere in the southern hemisphere. So let's talk about some specific storms. Hurricane Maria was devastating to the island of Puerto Rico. You've all probably seen these kinds of pictures, the utter devastation that this direct hit of a large Category 5 storm that hit Puerto Rico. And we've seen so many of these as of late. And they're unique. They're different from the garden variety hurricanes that we had been used to for decades and centuries. Hurricane Sandy, look how big it is. Hurricane Sandy, the eye of the storm is over the Atlantic Ocean, and it extends all the way out to Lake Michigan. Hurricane Sandy devastated, as you know, excuse me, New York City and the surrounding Jersey Shore and Long Island with weather that they haven't seen any time in the remote past. Hurricane Harvey was a stationary storm over Texas that dumped just totally unprecedented amounts of rain. There are areas near Houston that got 5 feet of rain. 5 feet of rain will cause substantially more than 5 feet of flooding. So it's interesting to note that 19 of the 20 hottest years on record have occurred since the year 2002. The exception is 1998, which was a stinking hot year and was the hottest year on record at the time that it was with us. And you'll notice this little mosquito. We'll get back to her later in the talk. So what are the 7 hottest years on record? They're the most recent 7 years. This is not due to chance alone. I would also point out that a little over a year ago, we had at Death Valley the hottest temperature reliably recorded anywhere on Earth. And 130 degrees, I will remind you, is the same temperature that you cook beef to get it medium rare. And if someone is out in that kind of temperature for very long, they too will be cooked to medium rare. So this is, bear with me with this, because although it looks a little complicated, it's not hard to understand. And it demonstrates so well what has been happening over the last 70 years or so. James Hansen is perhaps the most famous climate scientist, and he is responsible for the compilation of the enormous amount of data that went into this study. You will recognize this as a bell-shaped curve. The statisticians know it as a normal distribution. It's approximately a normal distribution. And this top point right here is the average temperature during the years 1951 to 1980, collected over all the land masses in the northern hemisphere during the summer months. So that is the spread of temperatures by geographic location. But instead of having degrees down here, we have a term that the statisticians are familiar with called standard deviations. And what's interesting about a standard deviation is that you can, by definition, you can say how many things are, how many events are one standard deviation or two standard deviations away from the average temperature. It turns out that in this range of -1 standard deviation to +1 standard deviation, 68% of all the temperature measurements will fall within that range. Within 2 standard deviations, 95%, and within 3 standard deviations, almost all, 99.7% of all the temperature measurements will fall between -3 and +3 standard deviations. So above that, you only have about 1 in 1,000 high temperature, extremely high temperature events. And the same is true at the other end, where you only have 1 in 1,000 extremely low temperature events. And in order to remember exactly where this graph is, when I start to change it, I'm going to put this green line in, which shows where that curve is. And we're going to move forward in time to 1990 to 2000. And during that decade, you can see that the graph has moved, the curve has moved to the right. That's one change that has occurred. You will also notice that the curve is a little flatter and wider. And now, instead of 1 in 1,000 events, you have considerably more than that occurring above the 3 standard deviation mark of 1950 to 1980. And you even have more down here on the cold side. We'll move forward 1 more decade, or actually 2 more decades, to 2010 to 2020. And when we do that, you will see this curve has moved far more to the right, and it's become even flatter. And now, instead of 0.1% or 1 in 1,000, we have more than 1 in 5 of these temperature measurements occurring in this range above what was 3 standard deviations from 1950 to 1980. And of course, as I said, it's not just the extremely hot events. You even have a few more extremely cold events, which can result in scenes like this. So let's talk about the other aspects of climate change. And floods and droughts have been increasing dramatically. All over the world, we have seen this. And the floods, it's obvious, there's more rain. And why is there more rain? Because warmer air can hold more moisture. And these torrential events happen, and they're much larger, and they occur less frequency because it takes some time for the water to accumulate. So that helps to explain why there are not only these flood events, but we are seeing more severe drought. And the reason for that is that with a warmer climate, the evaporation is happening faster. And we see vast areas of drought that were not affected by drought previously. Floods and extreme rainfall now occur substantially more often than they did in 1980. And we're not talking about just India or Pakistan or China. We're talking about a few hundred miles from here, where we have seen enormous flooding events. And the Potomac River is not supposed to overrun its banks by a mile. You generally can't go fishing near the Washington Monument and across the street from the White House, but this chap did fairly well fishing in the Potomac River, which had run its banks considerably. And the drought, really devastating droughts happening all over the world. And we're seeing an interesting situation in Southern Europe, where we've been growing wine and olives and all sorts of vegetation. The Sahara Desert has the potential of jumping the Mediterranean Sea. There are these wind current phenomena called Hadley cells. And the Hadley cells are expanding to the north and carrying desert conditions with them. And it is quite possible that we are gradually turning Southern Europe into a desert instead of the land that it is now. And of course, when you have drought combined with heat, you get the fires that we've been hearing so much about, particularly in California, but lots of other places as well. Not only are the fire seasons longer, but the fires themselves last longer, they're more intense, and they're harder to extinguish. Pretty soon, we're gonna have fire seasons in some places year round. And it's not just in temperate areas like California. We are getting an increased number of fires inside the Arctic Circle, within the boreal forests. And that's expected only to increase over the next few decades. So let's talk about public health issues. There are many public health issues related to climate change. Heat is the #1 killer of all weather events, more than tornadoes, hurricanes, and blizzards and any other weather event. Of course, we're seeing an increase in air pollution. The allergens thrive in this warmer weather. We're seeing food and water security diminished by the fact that some places are running out of water, which is obviously not just related to climate change, but food scarcity in many parts is related to climate change. Floods, we've already been discussing. Heart and respiratory diseases are on the increase, directly related to climate change. And of course, populations are being displaced because of sea level rise. But there are two diseases that I want to talk about in particular, because the connection to climate change is essentially indisputable. And one of them is Lyme disease. Now, Lyme disease is spread by a tick. The larval form is just a tiny little critter, but a lot of you either know people or perhaps even experience this. Here's a map from the CDC, which shows the individual cases reported to them in the year 2001. And watch what happens when you compare that to the CDC map of 2014. Let me show you that again. Here's 2001. Here's 2014. Now, one of the things, changing hats here for a second, one of the things that is classic for Lyme disease is the skin manifestation, these so-called target lesions. If you see something like this on you or a friend, run, don't walk to medical care. The thing about Lyme disease is that it becomes much harder to treat if you let it go. It is much more treatable if you get to it early. The second disease is the West Nile virus. And remember that little mosquito that I showed you back in 1998, which was the hottest year on record back when it happened? Well, certainly North America has been exposed to the West Nile virus many times before 1998. But that year and the following year, it was hot enough that it could take hold. There were two reasons why 1998 was such a hot year. One was climate change, but the climate change amplified a natural phenomenon called El Nino, which we don't have time to talk about in this talk, but it has to do with heat in the water being dissipated in the Pacific Ocean. But that has a worldwide effect on the weather. And El Nino combined with climate change resulted in that stinking hot year of 1998. And in 1999, we began to see cases of West Nile virus in the New York area and in the Chesapeake Bay area. That quickly spread across the country year by year until 2003, it had spread all the way across the country into southern Canada and into Central America, clearly related to climate change. I want to give you a brief history of climate science. I find this very interesting that this has been developing over 2 centuries. I could start even before then, but let's start with the year 1827 and the great French mathematician, Joseph Fourier. He is best known for developing what's called the Fourier series. And without getting into detail about that, suffice it to say that the Fourier series is programmed into every single cell phone on the planet. That's how important it has been to the development of technology. But he was also an astronomer and a physicist. And what he realized after doing calculations is that the Earth should be a much colder place than it is. It should be an ice ball, according to his calculations. And what he surmised from that is that energy from the sun passes through the atmosphere to warm the surface of the Earth. But dark heat, which we now call infrared, cannot so easily escape back into space. In other words, it gets trapped by the atmosphere. And here's a graphic of that. There's the sunlight in the yellow rays that are being warming the Earth, and the red infrared rays that are passing back out into space. This band right here, this blue band, that represents the heat trapping gases. And so you get some of this infrared absorbed by the heat trapping gases, and that causes the planet to be warmer than you would expect it to be if there were no heat trapping gases at all. Well, that's a good thing. We probably would not have life on Earth without some of the heat trapping qualities of the atmosphere. But let's move on to 1861. Dr. John Tindall, an Irish physicist, was very interested to know what gases in the atmosphere were causing that. And he developed this contraption where he could, through these valves, put the gas of his choice into this tube and pass infrared radiation through the gas and measure how much of it got through, and therefore determine whether infrared was being absorbed by that particular gas. He fully expected that the major components of the atmosphere, oxygen and nitrogen, which comprise about 99% of the atmosphere, that it would be one or both of those. He was surprised to find that that was not the case. What he did find was that these three gases were the ones that were absorbing the infrared radiation. Carbon dioxide, water vapor, and methane. And he published those results in the leading scientific journal of the day back in 1861, while we were busy fighting our Civil War over here. Moving forward, 1896, Svante Arrhenius was a Swedish physical chemist, and he is credited really with connecting the dots. Svante Arrhenius started thinking about this problem and undoubtedly could look out a window and see something like this. And he knew that we were dumping large amounts of carbon dioxide into the atmosphere. So he pulled out his trusty slide rule, and it took him a year to do all the calculations necessary to publish this paper in this same leading journal, to which he gives credit to Joseph Fourier and John Tindall for the work that they had done before. And what did he find? Well, he was unable to measure the exact amount of carbon dioxide in the atmosphere, but he posed the hypothetical: what would happen if you double the amount of carbon dioxide in the atmosphere? How much more heat trapping would be caused, and how much temperature rise would you expect? Well, in that publication, he predicted that if the amount of carbon dioxide in the atmosphere doubled, we'd see about a 5 to 6 degrees Celsius increase in temperature. He later modified those numbers. 10 years later, he published, well, it's probably closer to 2 degrees Celsius. Exxon did a lot of research on this back in the late 70s and early 80s, particularly, and they predicted from their studies that it would be about 3 degrees Celsius. They quickly buried that information. It was not good for shareholders. The Intergovernmental Panel for Climate Change has predicted that it would fall somewhere in that range of 1.5 to 4.5 degrees Celsius. So let's go back to our little graphic here. And so in the pre-industrial period, we were at 270 parts per million of carbon dioxide. That's about 250 years ago. And so keep an eye on this blue layer here, because we are going to thicken it. And now we are trapping more heat, and we're up to 419 parts per million carbon dioxide as of May of this year. Moving forward, Dr. Keeling. Some of you may have heard of the Keeling Curve, and you will see that momentarily. He devoted his career to studying carbon dioxide. First, he had to develop the instrumentation that can accurately measure carbon dioxide in the atmosphere. He created then an observatory as far away from civilization as he could reasonably get, and would measure mostly on a daily basis the level of carbon dioxide in the atmosphere. And after a few years, he developed this remarkable graph of all the data that he had collected. And what jumps out at you, of course, is this sawtooth pattern, this up and down. It's an annual pattern. And so what is causing the ups and downs of this graph? Well, it turns out that in the spring and summer in the northern hemisphere, the vegetation is growing. The grass is growing, the leaves are sprouting, and photosynthesis occurs. And that is pulling enough carbon dioxide out of the air that you see this downslope of the curve. And then comes autumn and winter, and the leaves fall off the trees and they decompose, and the carbon dioxide is released back into the atmosphere, and a similar amount of carbon dioxide is released. And so the cycle repeats itself the following spring and summer. But what you can also see here is this relentless year after year increase of the average amount of carbon dioxide in the atmosphere. And that is the signature of the burning of fossil fuels and the release of carbon dioxide. So let's look forward in time. Down here, there's that part of the graph that we saw, and that has continued relentlessly to the present day. And this is dated. We are up to 419 parts per million. And let's go backwards in time as well. And now we can see that when we go all the way back to 1700, we were down at about 270 parts per million, and now we're up at 419 parts per million in 2021. Now you might ask, okay, we could measure it there. How do we know how much carbon dioxide was in the atmosphere before we could measure it? And the answer are these little tiny bubbles, these air bubbles, which are in ice. Specifically, they are in ice cores. And the longest, deepest ice cores are found in East Antarctica, specifically in Vostok. And they're ice cores that are up to 2 miles long, have been pulled from the layer of ice over Antarctica. And when you look at the gas in those little tiny bubbles, you can measure the carbon dioxide level. And what that represents is what the carbon dioxide level was when that water froze. And when you go 2 miles deep in Eastern Antarctica, you are unearthing ice that is up to 800,000 years old. And when you plot the data that you get as a graph, this is what it looks like. So what you can see here, here is zero, which is really 250 years ago at the dawn of the Industrial Revolution, dating all the way back 800,000 years. And you can see this cycle every 100,000 years ago or so. We have these ups and downs. Well, what is that? Those are ice ages. And the ice ages happened on a regular basis about every 100,000 years. And this too represents climate change. But instead of being over decades, it's over thousands of years. This point right here is the end of the last ice age, when the amount of carbon dioxide in the atmosphere was less than 200 parts per million. And there was about a mile of ice over our heads here in Cleveland. I'm not sure what it was in Akron, but that was a very different climate than we are experiencing now. Where are we now? Well, before we talk about that, let's talk about temperature, because in those air bubbles, you can also detect what are called isotopes. Water molecules, for example, that are of a different weight because there are more neutrons. That also is a topic that we won't have time to get into. But suffice it to say that from those same air bubbles and ice cores, you can derive what the temperature was, the average temperature when that water froze. And lo and behold, you can see that there is a distinct relationship between carbon dioxide levels and temperature. Now, this is not a simple cause and effect relationship. If you increase the amount of carbon dioxide, you will increase heat trapping and you will increase the temperature. But the reverse is also true. There are ways that an increase in temperature will cause an increase in carbon dioxide levels. It's a complicated relationship, but what clearly is happening now as we dump billions of tons of carbon dioxide into the atmosphere, that is causing a rise in temperature. So here is what's happening to carbon dioxide levels. for 800,000 years and probably substantially longer, we have not seen a carbon dioxide level above, about 300 parts per million. And now we're up to 419 parts per million. So this is where we were back in 1957 when we started taking accurate measurements. And you can see this is just an enormous change in a very short period of time. But what happens if we continue doing what we're doing now and keep on burning fossil fuels at the highest possible rate? Well, we're going to be up to 600 parts per million. And if this point down here is the difference, up to here is the difference between weather as we know it and a mile of ice over our head. Just imagine what the difference in climate is going to be if we get up here. And in fact, it is quite highly questionable whether civilization can survive the violent climate changes that would occur if we get up to that levels. And that's why this is an emergency. Okay. The biggest problem is carbon dioxide. The other gases are problems too, but let's talk about carbon dioxide because of the massive quantities. So I want to show you a quick video here. And what this is a representation of carbon dioxide being released in New York City. Each one of these balloons represents a metric ton of carbon dioxide. Each one measures about 33 feet in diameter, and they are being released in New York City at a rate of 2 per second, every minute, every hour, 24 hours a day. 2 per second, another metric ton of carbon dioxide. Now, if carbon dioxide came neatly packaged in these blue balloons, or if it stank to high heaven, we would have done something about this a long time ago. After all, 1 hour of emissions would look like that. Presents a bit of a disposal problem. In a day, a single day in New York City, it would look like this. And after 1 year, you'd have a 55 million ton mountain of carbon dioxide produced by one city. But wait, there's more. If we look at China, the US, and the European Union, it's the equivalent to over 300 New Yorks, or 20 billion tons of carbon dioxide a year. But wait, there's still more. There are over 160 other countries. They are producing another 20 billion tons of carbon dioxide each year. So we've got a total of, and these numbers are old, so we've got a total of over 40 billion tons of carbon dioxide a year worldwide every year. So we are dumping over 110 million tons of a photoactive gas into the atmosphere every single day, and that is over 40 billion tons each year. What could possibly go wrong? Well, just about everything. So consider Niagara Falls for a moment for my next graphic here. Back in, let's suppose that we had a boat, in this case, a fireboat, coming down the St. Lawrence River. Now, in 1990, we really don't want to go over the waterfalls, and we have plenty of options. We could turn around and go the other way. We could go to shore, but we did not do that, and we wound up here, where our options in 2021 are substantially more limited, but we do still have options. For example, we could make it over to the shore here and a lot of damage has happened, and we have to figure out how to get our boat back, but at least we don't go over the waterfalls. If we choose a different path and we end up here, then this becomes inevitable. Now, I assure you that no lives were lost, or ships for that matter. This fireboat, 100-year-old fireboat, is safely docked in Buffalo, New York. And the wonders of Photoshop are simply incredible. I told you that I would talk briefly about methane. So there are two major sources of methane right now. One of them is the leaking pipes and valves and drilling sites that are releasing a lot of methane into the air. You may have heard about the satellite that detected this huge plume of methane from orbit coming from Russia. Well, this has been going on a lot. Airplanes have been flying over with infrared cameras and have identified lots of methane from the fracking fields and such. And the other source, as the climate warms, permafrost, which has been frozen for many thousands of years and contains frozen vegetation, is thawing. And as it thaws, the vegetation decays and produces methane. And here is a graphic example shown to us by the students at University of Alaska Fairbanks when they were looking for methane and found it. So change is happening, and it is too late to go slowly at this point. We can no longer move incrementally. We have to change emergently from the behavior that we are engaged in, which brings us to the most important parts of this talk. We already have solutions at hand. That wasn't true when I started giving these talks back in 2006. But wind energy, Texas is actually a leader in wind energy and is outproducing coal power by a growing margin. This is what wind energy capacity has looked like in the United States. You know, we're close to zero on this scale back in 2001. Look where we are in terms of gigawatts of power by the year 2020. Just an enormous change over time. And the same is true of solar power, where we're in some places, the amount of electricity produced by solar panels occasionally exceeds the amount produced by other sources. And this is what has happened to the world wide installations of photovoltaic panels. And you can see that we're essentially at zero all this time. And then the curve starts rising. This is exponential growth. This is what exponential growth can do. And meanwhile, here's what's happening to the cost of solar panels. So back in 1976, when President Carter put solar panels up at the White House, it cost $79 to put enough solar panel to generate 1 watt of electricity. Now it's 20 cents per watt. So a real life example of that, a typical installation at a residence would be a 5,000 watt solar panel. And that would have cost $397,000 back in 1976. Excuse me. Today, that would cost $1,000, installation not included. Now, consider the Kentucky Coal Mining Museum. They're no dummies. They were having trouble making ends meet as far as their budget was concerned. So what did they do? They put solar panels on the roof. They're saving several $1,000s a year by having solar panels on the Kentucky Coal Mining Museum. So it was projected that the market would grow just by 1 gigawatt per year by the year 2010. And what happened? Substantially more than that. And by 2018, we had exceeded that number by 109-fold. So as far as jobs are concerned, there has been tremendous growth in both the solar and the wind industry. And you can build solar panels in China. In fact, China is a leader building solar panels. But jobs that you cannot export, solar installer and wind turbine service technician, are amongst the fastest growing jobs in the US right now. So is there any precedent for such rapid growth of new technology? Well, I suggest you consider the cell phone. Here is the developer of the cell phone, Martin Cooper from Motorola, with his prototype. And AT&T did a study to try to figure out whether this was something that they should get involved with. And they did a study that forecast 900,000 users. And they said, okay, that's a go. We'll do that. Well, it turned out that the actual figure was way more than 900,000. And now there are more cell phones than there are people on the planet. So why were we not only wrong, but way wrong on this? 3 reasons I'll give you. One is that the dramatic drop in cost, the exponential decay of the cost. Hey, Jessica, if you're hearing this, can you bring me a glass of water? Always forget something. The quality has improved dramatically, and the low-income nations did not have landlines, so they've leapfrogged the old technology with new technology. I mean, after all, which would you rather have? This or this? So you'll always hear from the naysayers, but you know, the sun doesn't shine at night and the wind doesn't always blow. Yeah, I know that. What we need to do, and what we are doing quite actively, is developing storage for electricity. And the growth of that has also been exponential. You can see this in these numbers, and the scale here goes up to 3 gigawatt hours of storage, where we're going to change the y-axis to 1,000. And watch what happens to this part of the bar graph when we do that. It goes way down to the bottom, and there is no reason to believe that we cannot get to these kinds of levels of storage capacity in the next 20 years. Meanwhile, look what's happening to the prices on these things. They are getting cheaper and cheaper. And for that reason, you're seeing more and more electric cars. The transportation sector is a huge contributor to greenhouse gases. And electric cars will put a big dent in that. I wish I had time to get into the detail. You know, some people will say, well, you have to generate the electricity somewhere. That's true. But electric cars are far more efficient than gasoline-powered cars. And when we get the energy from solar, that's going to make an enormous difference as well. So the other thing that's happening is that the cost of electric vehicles, unlike the cost of gasoline-powered vehicles, is dropping very rapidly. And we're going to reach a price parity within the next year or 2, or maybe 3. And then it's all over, because electric cars are simpler in the kinds of quantities that we're talking about. They're going to be cheaper to produce. And here are the manufacturers that are already involved with the development of electric cars. And buses are a natural, because most buses are urban, and with regenerative braking, they will be far more efficient, and we won't get diesel fumes blown in our face as we're walking down the street. So here's the LA freeway. This is a totally unsustainable situation. Even if all these cars were electric, it would be an unsustainable situation. So we have to develop. Here you can see an example of intra-city trains. We need to develop these, and that hopefully is going to happen. In Europe and Asia, this kind of intercity train is taken for granted. These travel in excess of 200 miles an hour. They make it so that traveling by air is simply not warranted or necessary if you're traveling a few hundred miles. One nut that we have not been able to crack is electrifying air travel. The batteries and storage for electricity simply weigh too much. That being said, it is beginning. It actually is happening up in the Pacific Northwest. This is a prototype. This is an electric plane. The owner of Harbor Air is flying it. It was a 3-minute flight, but a very successful one, as you can see. There are no passengers, because even a single passenger would have made the plane exceed the weight limit. So obviously, this is still a work in progress. But Harbor Air is a great example, because they fly from Vancouver, British Columbia, to Victoria, to the Gulf and San Juan Islands, all within 100 miles or less, and Seattle as well. So if they can perfect this and get things lighter, they could actually electrify their aircraft. But it's going to be a while before we can electrify this guy. It's not going to happen anytime soon, at least not in that form. But consider this. Jet planes run on jet fuel. And the reason is that you can pack so much energy into jet fuel that the weight to energy ratio is very high. Excuse me, the energy to weight ratio is incredibly high. But carbon dioxide and water can be combined if you have a big source of energy to form jet fuel. This has been done not on an industrial scale yet, to my knowledge, but it has certainly been done in the laboratory. And if you can start to do this on an industrial scale, then you have jet fuel to feed to the hungry jet engines in this plane. And when they burn the fuel, they will produce carbon dioxide and water vapor. And this is, unlike burning fossil fuels, this is a closed loop. You use carbon dioxide to make the fuel, and then you generate carbon dioxide when you burn the fuel. And that will not cause the atmospheric levels of carbon dioxide to increase. So talk about strange things happening in the future. Consider this guy. So you may think, well, we're not going to see that anytime soon. This is a not lighter than air, but about the same weight as aircraft. This is not a real device. This is a synthesized video, but the company that is working on this, Verilyft, it's not just hypothetical for them. They are building the prototype right now in France for this. And they are saying that this production will produce an aircraft that can travel at 200 to 300 miles an hour, travel long distances, has the potential to be powered by electricity because the power system doesn't have to generate lift, just forward propulsion. And it doesn't even require an airport. You can lower things from this and at least as they envision it. We'll see what happens. In the meantime, look what's happening to coal consumption. Why is this happening? Because coal is expensive to burn, more so than solar and wind at this point. It is now cheaper to produce electricity using solar and wind. The only reason that coal is surviving as long as it has is because of the massive subsidies that you and I are paying to the power plants and the coal industry to keep them going. So getting back to those metric ton carbon dioxide balloons, this is where we need to be by the year 2050. We need to be carbon neutral. And that gets us to what can we do? Well, there are lots of things we can do as individuals. For example, we can change light bulbs. But you know what? Changing light bulbs is not going to get us there. We need to do a lot more than that. And we need to do it collectively. Most of us as individuals can't make a whole lot of difference. I mean, there are some notable exceptions to what one person can do, but we're not all Greta Thunbergs. And the best thing that we can do is get involved with organizations that amplify our voice by the millions. And I am going to talk about certain organizations. You do not need to copy any of this down. We will provide you a link very shortly with the organizations that I'm talking about here and how you can get in touch with them. I put these three organizations up here not because they're somehow better than other organizations like, say, the Sierra Club. I put these up here because these are organizations that I am involved with and know better than any of the other organizations. So the Climate Reality Project is the organization I have to thank for being with you today. They provided the training back in 2006 and provided me with a lot of the images that you've seen here in this talk. As I give these presentations. They're an educational nonprofit, and back when I went to Nashville, Tennessee and spent a long 3-day weekend up close with Al Gore, climate scientists and speech coaches. Since then, I was the second group. There have been hundreds of groups since then, and instead of only 300 people trained, there are now thousands, maybe tens of thousands of people trained by the Climate Reality Project to give presentations like this. The second group I want to talk about is the Citizens Climate Lobby. The Citizens Climate Lobby is a lobbying organization, and they are focused like a laser on getting federal legislation signed into law that not only puts a price on carbon, but immediately distributes those dividends to the public, to individuals in the form of a check every month or every quarter, reimbursing people for the money collected for the carbon emitted. The third organization is a highly political youth group, the Sunrise Movement. They are strong proponents of a Green New Deal. They are politically very active and have done sit-ins, which have gotten the attention of many politicians. And I was involved with helping them out as they were beginning to give talks in the Cleveland area and in Northeast Ohio. So that's on the national level. As I said, don't even think about writing these down, so you'll be able to get them. And these are groups in Cleveland. I'm sure there are similar groups in the Akron area, or maybe these groups have a reach into that. But let me just run through them real quickly. And again, you can take a closer look at any of these that may strike your fancy. So let's consider this. In the past, we really didn't understand the severity of the problem that we were dealing with. And if we don't do anything about it, the children, the people who are children now, in the future, will be powerless to prevent really catastrophic things from happening. So it's up to us in the present to buckle down and make things happen. I'm going to give you 3 things that we as individuals can do. Thing number 1, vote. Thing number 2, vote. Thing number 3, persuade somebody to vote or get involved with the organizations that are registering people to vote, because some people don't get around to it. And if you get out there, there are groups that have registered thousands of people in Northeast Ohio. And we've got to do this because it turns out now that every election is a climate election. And we also have to take to heart what Franklin Roosevelt said. We can't stop once people are elected. After they're elected, we've got to keep after them, and we've got to make them do it. And as another leader from that era said, thank you very much for your attention.
Thank you so much, Dr. Schreiber. Can you hear me on this? Thank you so much, Dr. Schreiber. We really appreciated your talk. And we have a couple of questions. Anybody else, please feel free to add any questions that you have. I wanted to let you know a couple of the questions that we got were, you said that it's 5,000 watts for a residence and that the cost is about $1,000 plus installation. Somebody said, Sarah added, that she would love to get solar for her house, but no one will give her an estimate. Do you know any companies in the area that could help out?
Oh, boy. I'm surprised you can't get any estimates. There are, the name Third Sun Solar comes to mind, but there are others. I know that there are others. Unfortunately, I could try to get back to you with a list of companies.
Oh, goodness, that would be great. Thank you.
That do that, but they're not hard to find. I know they're out there. I actually live in a condominium with 147 units here, and we've actually been talking. Now, obviously, it's a different scale, but solar installations have occurred. There's at least one church in Shaker Heights that has installed solar panels. But let me talk about some of the differences in ways that you can install solar panels. You can go, some people are not in a position to go out and spend several $1,000s to buy the solar panels and get them installed and own them and maintain them. There is at least one other way to do that. There are companies out there that will own the solar panels. They will install the solar panels and they will take over your utility bills. And your utility bill may stay the same, it may drop a little, but you will have solar panels that are owned by the company, and they can actually make a profit for themselves and cost you no more and perhaps less money per month by doing that, because solar energy is in many cases cheaper. Now, unfortunately, there have been roadblocks as far as the legislation that has been passed that make this more difficult, but it can be done, and I know those companies are out there. I will see what I can find. I will get some more information and forward it to you.
Thank you. And William Lang had a question about whether any studies have been done on the effect of the disposal of spent lithium-ion batteries and what effect they have on the environment.
Sure, that's a big topic, and the ingredients within the batteries are becoming less and less toxic all the time. The older generation of batteries had some rare earth elements in them, and they are being phased out. But more importantly, there are new technologies coming down the pike. There may not be enough lithium on Earth to create all the lithium-ion batteries that would be necessary if that were the only kind of battery out there. But there are things that on the horizon. Probably the leader is zinc-ion batteries. Zinc is far more prevalent on planet Earth than is lithium. And zinc-ion batteries are not scalable to automobiles, but they are very promising for stationary installations, the kinds of installations that power plants would use to store solar energy overnight, for example. And that's one technology. The chemistry of lithium is not that different from the chemistry of sodium. Sodium is incredibly prevalent on planet Earth. All the salt in the ocean is sodium chloride. And there is some promise with that. But that is developing more slowly than the zinc ion technology, which is coming right along. So yeah, there are a lot of people working on ways to recycle these batteries and ways to be less damaging in the mining process. But it's an issue. It's a real problem. Now, compare that to the issues surrounding the disposal of nuclear waste. Compare that to the problems of mining coal, fracking for natural gas, or drilling for oil with the oil spills that seem to be inevitably related. What most people don't know is that a fairly significant oil spill occurs almost every day. We hear about the huge ones, but we don't hear about the ones that are occurring all the time. And so everything is relative. Of course, there is an issue with lithium, but consider the other issues and the alternatives.
And any updates do you know about the possibility of an infrastructure for charging stations for cars?
That is growing incredibly fast. Tesla is far and away the leader on this. Tesla has something like 25,000 charging stations out there. And although although I'm not familiar with how this is done, my daughter tells me that their plug-in Prius, they have a Tesla charging station practically next door to them, and they have an adapter that they can use to charge. So there are ways to take advantage of the Tesla charging stations, even if you don't happen to have a Tesla. Also, there are networks of charging stations, but those are under 10,000 in number in the United States. But I can assure you, They are growing incredibly rapidly. And exponential growth is an amazing thing. And that is what we are seeing with the charging stations. Does that answer the question?
Absolutely. And Dr. Schreiber, thank you so much for being with us tonight. That brings to a close all of the questions that we've received to this point. We really, really appreciate your being with us and sharing so much valuable information. And thank you again to everyone who's joined us for tonight's conversation. I hope you get a tall, cool glass of water soon, Dr. Schreiber. And thank you again so much for being with us and for sharing this valuable information and for all of the work you do to share this war. Yeah, and somebody said this talk should be required viewing. Well
thank
said,
you.
Sarah.
And thank you all for listening. If there's any other specific topic that you want me to talk about, go into greater depth on something, we can talk.
I'm sure we will be reaching out. Now, I wanted to just make everyone aware who's still with us that Dr. Schreiber does this of his own volition without asking for a fee. And so I would encourage anyone who feels moved by the topic to certainly download the link to the organizations that he shared and to consider making a donation to support one of those groups and this effort so that we can all care for the environment so much better. And the next 20 years, we're going to make a difference.
Oh, yes.
Thank you again, Dr. Schreiber.
My pleasure.